it would be wise, I think, to begin preparing for that, as you will. You don't have to cram all weekend, but set aside an hour or so and begin looking at the homework, looking at the notes. I'll make sure the concept tests are posted today. I'm not sure that I have them posted just yet. But, taking a look at those things so that you probably have other things on that Monday that are coming up or that week. I know it's getting to sort of be crunch time. It is for me too. But take this weekend, it's a little bit quieter maybe than others. And I don't know, eject yourself with a 5 news article a little early and go home and study physics or whatever you can set aside in that one. Okay? All right. Well, let's see. Did we do this question? Yes, we did. Okay. Where did we leave off? Did we do this one? All right, let's try this. Consider these two separate arrangements. If Q3 is negative, what is the charge of Q1? All right, I'm going to stop at 40. 40. Okay, I think that's right. Let's double check. So Q3 is negative. Yeah, that's right. So if this is negative right here, that means this has to be positive. So if this is positive, then that is also positive. All right. Basic properties of charge. On the test, you'll see a few multiple choice questions about the basic properties of charge. They're quantized, like charges repel, opposite charges attract, that sort of thing. We've seen some questions like that along the way, and we'll see a few more. Let's see, where do you find a dog with one leg? I know we have a lot of animal lovers, so please don't be offended by this joke, but where do you find a dog with one leg? Right where you left them. Is that mean? That's kind of mean, isn't it? No. Okay. Right, let's look at Coulomb's law. Listen, Coulomb's law, we did Newton's universal law of gravitation. This is practically identical. And you're going to see some of the same stuff, 2D vectors and the like. So you mastered Newton's universal law of gravitation, you've mastered Coulomb's law, basically, because it's just 2D vectors, and the form of Coulomb's law is the same as it is for Newton's universal law of gravitation. Coulomb's law describes the forces between two charges. It is F equals K Q1 Q2 over R squared. See, it looks just like Newton's universal law of gravitation, except our G is now replaced with Coulomb's constant, K. K has a value of 9 times 10 to the 9th. Or, in your calculator, 9E9 is probably your preferred way to put that in. That's in Newton meters squared per Coulomb squared. Q is in units of coulombs. That's our SI unit for charge, capital C. And then R is in units of meters, which is our SI unit. R is just the distance. It's not a radius of the charge. It's just our distance between our two charges. Notice the relationships. So if I increase, say, Q, then F is going to increase. If I increase R, let's do that in blue. If I increase R by a certain amount, then F is going to increase by a lot more because it's a 1 over R squared dependence. So we'll see on the concept test questions like, well, if you increase Q by a factor of 4, how does that affect F? Or if you increase R by a factor of 2, how does that affect F? Those sorts of things, just exploring the mathematical relationship between those variables. All right? As I said, and charges are often very small. So remember these metric prefixes especially. You still need to know all those other metric prefixes. Just to remind you, we had nano, micro, milli, centi, and then crossing over to the bigger side, we have kilo, mega, and then we'll see giga later. But this is 10 to the minus 9, 10 to the minus 6, 10 to the minus 3, 10 to the 3rd, 10 to the 6th, and 10 to the 9th. And then we just sort of throw in centi because we use it quite a bit. 10 to the minus 2, 1 over 100. There are 100 centimeters in a meter. You know those metric prefixes, but especially if we're dealing with charges that you know, micro and nano, because charges are often really small, right? The fundamental unit of the charge is 10 to the minus 19. So when we're talking about charges, we'll often use those prefixes. As I said, Coulomb's law is similar in form and action to Newton's universal law of gravitation. I'll just say gravitation. And so actually in chapter, what I'm calling 0.5, which is not going to be on this next exam, we'll do a lot of the same stuff we did in chapter 0, dealing with flux and Gauss's law, which will also apply to electric fields and forces. So we'll see that again. It's good and it's bad because it means, you know, we sort of have the same material on exams 1 and 2. If you do well in exam 1, you should be good on exam 2 as well. All right? So we'll see a few other things as well. Now, Newton's third law also applies here, just like it did for Newton's universal law of gravitation, so that if I have a force on charge 1, then the force on charge 2 is equal and opposite, you know. So here I have two positive charges. Attractive, repulsive, what's the force? Right, they're going to be forced away from one another. So these forces, F on 1 due to 2, F on 2 due to 1, they're going to be equal in magnitude. Opposite in direction, but equal in magnitude. And then similarly here, F1, 2 is equal but opposite F2, 1. And that's a nice outplane of Newton's third law, that anytime I have a force, even if there's no contact between the objects, I have an equal and an opposite force, this action-reaction pair. All right, superposition principle. We're going to go through this one more time. This is sort of our last time to see vectors in this way. We'll see vectors again, but not doing 2D stuff like this. So for example, first do a little 1D problem. If I want to know the force on Q3 here, I imagine Q2 exerts a force and Q1 exerts a force. Why don't you go ahead and sketch in the vectors that are affecting Q3. Now we have two force vectors here. One due to Q1, what's the direction of that? And one due to Q2, what's the direction of that? Go ahead and sort of sketch in those vectors, trying to get their relative size is correct. You know, one might be bigger than the other, or they might be about the same size. But think about how they should be related to one another. F32, is it left or right? That is the force on particle 3 due to particle 2. Is it to the left or right? It's to the left because this is a negative particle, this is a positive particle, so F32 is to the left. F31, left or right? Nothing. That's right, it's going to be to the right. F31 is to the right because that's positive, this is positive, so they're going to be repulsive. So if I want to know the net force on this charge, all I have to do is calculate this force and take the vector sum. And the vector sum is just going to be, you know, the difference of those. So I'll go ahead and show you F31. I'm not going to do it for F32, but it's going to be 9 times 10 to the 9th. That's 99. Q3, which is 4 coulombs. Q1, which is 2 coulombs, divided by the distance, which is 3 meters, and then it's squared. And so this cancels. I get some things that cancel out. I get that canceling with that, and I get 8 times 10 to the 9th newtons. Notice I use coulombs for charge. A coulomb is a whole heck of a lot of charge. I just did it to make the numbers work out easily. But on the test and in your homework, you'll find that we use nano or micro coulombs to designate charge because that's just more. physical, more realistic. All right. And then if I want to find F32, F32 is similar. In a similar way, I find F32, and it is I'm sorry, did I make a mistake here? No? I have a mistake in my notes, I think. All right, so F32 is going to be 9 times 10 to the ninth, 4 coulombs, 1 coulomb divided by 2 squared. So this cancels there, and I'm left with 9 times 10 to the ninth. All right, so if I find the net force, the sum of the forces is F31 minus F32. And that's equal to -1 times 10 to the ninth. 8 times 10 to the ninth minus 9 times 10 to the ninth. What's that like? 8 billion minus 9 billion. So it's -1 times 10 to the ninth newtons. So the net force on this object is in this direction, and it has a value equal to 1 times 10 to the ninth newtons. You will see not one-dimensional problems on your exam. You're going to see two-dimensional problems. But you can see some conceptual questions that follow the same idea, where I ask you, where can you put a force where can you put a charge that would have 0 force? And you have to go through the process of figuring out, what are the vectors and thinking about them qualitatively. We'll do some questions like that in just a little bit. But let's go through this, though. I want to know, what is the force on Q3? Just like we did before, okay, I'm going to skip through some of the steps or go quickly through them because it's exactly what we did before. And in fact, we're going to see another 2D problem before we get out of this chapter as it deals with fields. But just take this as a time to make sure that you got this because it will be on the test. I want to know the force on Q3. I have 2 forces acting on it. One is in this direction and one is in this direction. Right. I just know that because of the relative signs of the charges. I have one attractive force and one repulsive force. I want to draw my coordinate system. Looks like that. I want to go ahead and figure out my angles. Notice I have a right triangle here. It is a 3, 4, 5 triangle. And if you don't know your 3, 4, 5 triangle, that's okay. But it's a fairly common triangle to use. And in the 3, 4, 5 triangle, the angle opposite the 3 side is 37 degrees. And so that means that this angle is also 37 degrees. All right? Because I have these, 2 lines crossing, and those opposite angles are the same. Okay? Now I want to know what is F31. This is F31 right here, and this is F32. So I just need to find the magnitudes of those forces. F31 is K Q3 Q1 over R squared. It's going to give you that value. It's 1.08 times 10 to the minus 9. And F32 is 1.13 times 10 to the minus 9. These are both in newtons. So now what will we do next? I've determined the magnitude of the vectors. I've drawn my coordinate system. I've determined my angles. What would be my next step? Think about it. Don't say it out loud, but you have a question?
Why is it 10 to the minus 9?
For which one? F31?
Just both of them.
Oh, I skipped that step. So let me, I'll sort of sketch it in a little bit. I found F31. F31 is equal to 9 times 10 to the ninth times Q3, which is 1 times 10 to the minus 9, times Q1, which is 3 times 10 to the minus 9, divided by this distance, which is 5 meters, squared. And that just equals 1.08 times 10 to the minus 9.
Where are you getting the 1 times 10 to the minus 9 and 3 times 10 to the minus 9?
Oh, Okay, good question. So here, these are in nanoprotons.
Okay,
All right.
that makes sense.
Yeah. Sorry, I'm skipping over several steps as I go along. Okay, so let's go back to that original question. What do I do now? What's on to that next step? Well, what do I need to do? I want to get to a point where I can just add up the x components and add up the y components. But I can't do that just yet, right? I want to resolve the vector, right? I need to resolve that F31. So to do that, I like to draw pictures. So I draw this picture here, and I'll go ahead and sketch in F32. And then the x and y components of F31. That's F31 sine of 37, F31 cosine of 37, and I can calculate those. I do the sum of the forces in the x. That's F31 cosine 37. I'm just going to call that F31x minus F32. And putting in those values, which I'm not going to do, but I say this times cosine 37 minus this, and I get negative 2.67 times 10 to the minus 10 newtons. And then the sum of the forces in the y, well, that's just F31. That's a sigma. The sum of the forces in the y is F31 sine of 37, and that's equal to 6.5 times 10 to the minus 10. All right, so now what I have is I have my x and y components. Draw another picture. My x component is in this direction. My y component is in this direction, and so my resultant will be in that direction. So I need to do two things. I need to find its magnitude, and I need to find its direction. To find the magnitude, I do the Pythagorean theorem. Square root of 2.67 and that's equal to 7 times 10 minus 10. So that's part of the answer. And then the other part of the answer is to find this angle. You can express that angle in a couple different ways. We could also express it from a positive x-axis, but I usually like to express it from whatever x-axis is closer, the positive or negative. And so phi is the inverse tan of f, is it fy over fx or fx over fy? Fy, right, because that's the opposite side, so Katoa, and that is equal to 67 degrees above the negative x. All right, I know many of you have mastered 2D vectors, but if you haven't yet, make sure you have. If you have a 2D vector, it'll either be gravitation, forces, or fields. And you have homework problems on all of those that you sort of go through it. Okie dokie? Maybe something like this. I might try to make it a little simpler with the numbers and the like, but it'll be similar difficulty. Y'all good with that? It's fairly important that you go away knowing how to do vectors, so sort of take this as one last opportunity. All right. You'll also have some questions like this, where I just ask you to think about the vectors and what they are. Which of these is the best represents the net force on the rightmost charge? Which do you think is the best answer for this? In fact, just to make it a little more clear, I'm going to make this, instead of being -4, let's make it, I don't know, -6. A little bigger than it is. way you approach these, you want to sketch in the vectors that each of these charges cause on this charge, and then ask yourself, what is the net result of those two vectors, the sum of those two vectors? All right, let's stop at 115. 115. Okay, good. E is right. You want to sketch in the vectors. So I have, due to this charge, I have a force that's in this direction. And then, due to this charge, I have a force that's in this direction. This force is a lot bigger than this force for two reasons. What's the first reason? It's the most obvious. It's a bigger charge, right? What's the second reason that the force is bigger? It's closer. So the closer actually has, well, goodness. I tell you about quiet, man. How she sneezes. I told you that she is like the loudest sneezer you've ever heard in her life. Like, when we first got married, we were in the car, and she sneezed, and I thought it was going to pierce my brain. It was just the right frequency. And I sort of told her, very loud, so I can't stifle my sneezes. But now when she's around me, she tries to stifle her sneezes. But sometimes when I hear her in the other room sneezing and she's like all alone, like nothing you've ever heard before. Okay, what was I saying? Oh, it's closer, so the force is bigger. This red force, due to the -6q charge. And then the sum of those two vectors, because the -6 gives such a large charge, it swings that net vector all the way over to E. You might have put D. I maybe put D. Okay, one of you. Whoever that was, I can sort of understand why you would put D, but because this force is so much bigger, it is going to pull that vector closer to that vector. Now let's try this one. What's the magnitude of the force on the -6 nanocoulomb charge? In case you can't see this, this is a +3, and this is a -6 nanocoulomb. Remember, nano looks a lot like 9. It's small, so it's 10 to the -9. If you finish this one, go on to the next one for the direction. All right, let's try to wrap this up soon. Maybe 20 more seconds. Feel free to ask your neighbor. Looks like many of you have settled on the same answer, which looks to be right. Yeah. I'm going to stop at 220, 220. Okay, I'm pretty sure A is right. Let's see. First thing you want to do, y'all, is you want to figure out what is this distance, because that's going to be your R. And your R is going to be the square root of 0.5 squared plus 0.5 squared. And that turns out to be 0.71. Or you could say that it's the square root of a half. I'll show you why in a second. And then we say our force is KQQ over R squared. And so that's 9 times 10 to the 9th. Or 3 times 10 to the minus 9. 6 times 10 to the minus 9. Divided by the square root of 0.5 squared, which is just 0.5, right? And then you find that that is equal to 3.2 times 10 to the minus 7. All right, so A is the right answer on that. Make sure that you can, solve for these forces. This is just a small part of the bigger pre-response problem that you'll have on your test. Now let's try to find the direction on that charge. The direction, what is the direction of the force on the minus 6 nanocoulomb charge? Be careful, look at the axis designations. Make sure that you're measuring your angle correctly. So notice it's a special triangle that we're looking at. Should help you. All right, let's stop at 55. 55. Just guess if you're not sure. We'll stop at 50. Okay, 50. Just a couple more seconds. Okay, A is the right answer. Listen, you really need to be careful on your axis designations and how we measure these angles. On the test, it's not going to be that big of a deal because you'll make up your own designation. But in this case, I know that my force is in this direction. And so I also know that this angle is 45 degrees. So my first thing would look and see, well, is it B? It's not B because that's above the positive x-axis. And it's not D because that's below the positive x-axis. And this would be above the negative x-axis. And then it has to be one of the others. It's not going to be 30 degrees. So let's think about this A. Well, if I look at my coordinate system like this angle is from the positive x-axis. That's 180 minus 45. That's 135 degrees. So usually, we measure angles in two different ways, usually from the positive or the negative x-axis. From the positive x-axis is sort of the same. Okay? Let's see. We're not going to do this quick test on the next page, but I'm going to go ahead and give you the answer so you can try it on your own. It's just like what we did before. The magnitude of the force the magnitude of the force is 0.0098 newtons, and the angle phi is 82 degrees. Give me just a moment. Let me look at something. We're not going to worry about part B here. You might see some conceptual problems where it asks, where can I put another charge such that the force on it will be 0? We'll see some of those later, but don't sweat it right now as to having to calculate for that. Okay, but do know how to add up two vectors like we've been doing. Okay? All right. Let's see. I brought the Van der Graaf generator today. Try that problem out on your own. There's some examples in your homework too. Well, let's look at the Van der Graaf generator. we talked about electric charge already. And this is a device. What this does is like stand up. What this is it has a belt. When you turn it on, this belt goes down into the metal base, and it rubs its feet on the carpet, right? You rub your feet on the carpet, and then you shock somebody. That's how you snort on there. Yeah, so what this does is the belt goes down inside this metal box, and there's like these little brushes that rub up against it that deposit electrons onto the belt, and then it comes up into the metal ball. You see the little wires there? They deposit those electrons onto the sphere. It's called a Van de Graaff generator. See that? And it just allows you to have a bunch of charge on this metal sphere. So I also have a discharge sphere here. This is a discharge sphere. It has a little wire attached to it. It goes to this metal rod. When I say something is grounded, we talked about this already. It doesn't mean that it doesn't get to watch TV or whatever, but that it is actually connected to the ground. And we'll talk about grounding and how that works in your house, because your house is grounded. It's connected to the ground. That third prong is in your outlet. The little round hole in your outlet, that's the ground. It connects your devices directly to the earth. And that's what we're doing here. The earth is like this big reservoir of charge. You can put all the charge you want into it. It doesn't really change. It's like, pouring a cup of water into a big lake. It doesn't really change the thing. So I can turn this on. Hit the lights on there, turn them off. Oh, there we go. It is really dry today, so they will build up a lot of charge. See this part? It's like it reminds you of Chris Reed's. Listen, it takes about, for an electron to jump across an inch of air, it takes about 10,000 volts. So this is about 40,000 volts because it's jumping across about 4 inches. Yeah. You can also see the discharge sphere. It sort of jumps a little bit. When there's electrons jump across, you get a charge. Who wants to talk? Alright, you can take the lights. Alright. So you always done the thing with your hands on the thing and your hair all standing up? You might want to try that. Sadie, Hillary, I know good hair part. Light colored hair is that's it's light. Jesse? Anybody? Any of the guys want to do it? Yeah, it wouldn't really work. It would work sort of, but it's still cool. Let me move this wire, because really anything that's near the conducting, you're going to become like really charged. It's not going to hurt. It's not going to kill you. Okay? It's not going to hurt. Come on. Just put your hands here. Just put both hands there. And it's important that when you step off, that you hold your hands up like this, that you don't have to touch anybody for a minute or so. Okay? Are you comfortable? How do you know? It's a particularly dry day, so there's just a lot of charge in the air. But Brennan has curly hair, and curly hair is thicker, and it just doesn't move around as much. I saw one of their girls. I sort of see a few little hairs coming up. You'll see them. They're trying to stretch out. They're trying to go out because they all get negative charges on them, and they're repelling to one another. So they're dumping lots of extra electrons. You can take one hand off if you want to sort of run it through your hair. Yeah. I mean, I can see. You'll see the little hairs trying to straighten out on the top. How do you feel? A tingle or anything? Is it tingle? How? Reach out and touch. No, no. So probably. And then just make your hand off like this, and then step off. Feel anything through your feet? Now, sometimes people will feel the charges leaving their feet because they'll go straight into the ground. All right, anybody else want to try? What? Well, I'll show you. I'm going to show you else. Can somebody stand here? Look, I don't have very long hair, so I may just think. All the way. All the way. It's complicated. There's my, all right, go ahead, we'll turn it on all the way. And these wires, they're short circuiting wires. The charges will, when you get too close to the electrical wires, they'll jump off. Can you take that discharge here? That's here. Alright, so you ever use like a lightning rod, or you have lightning rods like in your house? A lightning rod just allows a place for the charges to escape into the atmosphere. And so this is like a little lightning rod. Look what happens when I hold it up. And then if I put my finger over it, I'm not allowing the charges to escape. I can sort of put my finger over it a little bit. Go away. And then come back. Actually, when I'm doing this, they're actually jumping onto the roof. As I get closer to that metal, they'll jump onto the roof. Alright, you can turn it on that really quick. Right here, the charges are down. Okay, one more thing. We're going to get into electric fields. And I have this device that we use to map out the electric field. This is just a styrofoam cup, but inside I bought these things that you buy on these like science websites. They're like electric field mappers. You ever seen Twister, like from the 90s? The movie with the tornadoes? You ever seen that movie, seriously? Where they put the little balls into the tornado and it maps. It's sort of like that. Like these are going to map out the electric field. Now the electric field is a measure of force. If you're in the lab, you've all done the electric field lab. But this will map out the electric field. And as you know, you're going to have this electric field that's sort of going to come out, and actually it's going to come back around because you have both positive and negative charges. Well, let's take a look. This is going to map out the electric field. All right? You sure? Pretty cool. Don't pick up any of those special electric field numbers that you do. All right, guys, Dr. Now let's see. All right, we're going to get into electric field. Just sort of a little bit about the exam first. So the exam, I think that next week that we're going to get into the next chapter, and so we'll sort of play that by ear as to how far we get into that chapter. It's kind of a short chapter, and like I said, it's a repeat of chapter 0, so we'll sort of address that when we get into it next week, okay? I don't want to put too much information on the exam, of course, but, you know, we want to use our time wisely, too. So, for now, just look at chapters 0 and 1 if you start studying over the break. All right, well, first, the electric field. The electric field exists in the space surrounding a charged object. We use the electric field to define the force, and the electric field then, it's a vector quantity. It is defined as the force per unit charge. I'm going to introduce this idea of Q naught, where Q naught is a positive test charge. Turns out the electric field, like this equation, will hold for negative charges too. But we're going to use this idea of this positive test charge to help us map out the electric field. So in our minds, just think about what does the electric field look like around this positive charge or this negative charge or this group of charges. So this is a positive test charge. It's imaginary. It doesn't really exist. My physics teacher said you have to carry around in your back pocket. What are the two things you always carry in your back pocket? Have I told you all this? I think I have. Your right hand and a positive test charge. And they're both imaginary. Well, your right hand's not imaginary, but the positive test charge is imaginary. The units of the electric field, just based on that definition, are newtons per coulomb, or we're going to see next chapter that it's also volts per meter. And we'll look more next chapter at the relationship between newtons, the electric field, and what we call the potential. When a charge Q is within an electric field, the force that the charge feels is given by this. F is equal to Q times E. And that's based on the definition of our electric field, because remember the electric field is a force per unit charge. And so our force then is just the charge times that force per unit charge. Electric field is just this thing we make up. We use it to describe the forces that particles feel when they're around other charges. It's just sort of something we made up to help us describe the forces. Let's try this little quick test. You'll see some homework questions that are similar to this. I think you have like an inkjet printer in your homework that's similar to this, where you use these electric fields to accelerate charged particles that are on ink. But here we have a proton accelerated from rest in an electric field of 100 volts per meter. What is the velocity of the proton after 2 seconds? Stop at say 15 more seconds. Stop at 120. I'll give you a hint. Yeah. So I want to know the velocity. So there are a few steps that you take here. First of all, have this particle. It's going to accelerate. It's going to accelerate based on the force that it feels. The force is Q times E, right? So first you want to find the force. I have the electric field. I know the charge of a proton. It's 1e, 1.6 times 10 to the minus 19. And then I also know that F equals m times a. So if I have the force and I have the mass, then I can find the acceleration. And then I'm looking for its velocity. So I say v is equal to a times t. It's initially at rest, so there's no v naught. I'll give you another moment. By the way, on the test, I give the proton mass here, but all that stuff is on the equation sheet, so I won't give you any constants in the problem. I'll give you a little bit longer.
What's the charge of the proton again?
It's 1.6 times 10 to the minus 19. That's your fundamental unit of charge, 1e. That's on your equation sheet. This may seem just like an exercise, but it's actually fairly important, especially for you chemists, because, you know, like the mass spectrometer operates by this idea that you accelerate a particle, a charged particle, through an electric field, and then you use magnetic fields to determine the curvature of the mass-to-charge ratio. It's important, like in cathode ray tubes, like you use the old TVs, they use electric fields to accelerate electrons to a certain speed. All right, we'll stop at 3:15, okay? 3:15, is that enough time? Have y'all just guessed up till this point? Or you just guessed? You got it.
I got it.
Everybody ask Brennan. He put.
Right now.
No, it's all right. You can tell people if you want, but I'm going to stop at 3:23. Okay, I think that's right. Yeah, that's right. So F is QE. So the force on this particle is going to be 1.6 times 10 to the minus 19 coulombs times 100 volts per meter or newtons per coulomb. Either one of those units is fine. And then the acceleration is F over m. That's going to be 1.6 times 10 to the minus 17. That's the force, divided by 1.67 times 10 to the minus 27. And then you say V is equal to A times T. This is the time, and so V is 0.9 times 10 to the 10th. You wouldn't actually, in a real, say, mass spectrometer, it wouldn't get up to that speed because, you know, that's beyond the speed of light. It wouldn't actually travel for 2 seconds. It would travel for a much smaller time. I just use that to make the numbers easier. Okay? We'll see that again when we get into magnetic fields. And I think we're out of time, but y'all have a great weekend, okay? So I'll see you. Think about your exam a little bit. I'd really like to see y'all having mastered chapters 0 when you go into next week.